All right, guys, so this is section 7, topic 6 on transformations of exponential functions. Now, transformations of functions should sound familiar to you. We have done them with linear. We talked a little bit about them with linear. We talked about them extensively with quadratics and absolute value functions. So all of this should seem pretty familiar to you. It just all throws back to the same basic premise. So we have the exponential function. This is going to be our base for the lesson, which is f of x equals 2 to the x. So f of x equals 2 to the x is my base there. We know that this was the same thing as f of x equals 1 times 2 to the x. So that 1 represents that y-intercept right here, and that 2 represents that common ratio of as we go over 1, our y-coordinate is multiplied by 2. So as I go over 1, 1 times 1 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and so on. And as I go to the left, it's opposite. Instead of being multiplied by 2, it's being divided by 2. So 1 divided by 2 is 1/2, 1/2 divided by 2 is 1/4, 1/4 divided by 2 is 1/8, 1/16, 1/32, and there's that asymptote of x equals 0. Of y equals 0 that we discussed before. Because remember, this is the line y equals 0, this is the line x equals 0. So to talk end behavior, just to kind of recap here, as x increases, as x approaches infinity, y approaches what? You're right, it also approaches infinity. So as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches 0. Okay, so x approaches negative infinity, y approaches 0. So then, consider the following transformations of f of x. Write a function to represent each transformed function and describe the transformation. So negative f of x. So we're still going back to the basics of f of x equals 2x. Well, if f of x equals 2x, let's write it over here, or 2 to the x, I'm sorry, then negative f of x would be negative 2 to the x. Okay, so my transformed function here would be negative f of x equals negative 2 to the x. Okay, so what happened? Let's look at both of these. So it was up, it was going through 1, now it's going through negative 1. It was going through 2, now it's going through negative 2. It was going through 4, now it's going through negative 4. Okay, so all of these, what has happened to all of these points? Okay, so the graph was reflected across the x-axis. So just like on my quadratics, when I had x squared versus negative x squared, or 2x squared versus negative 2x squared, if it was facing up, this negative in front of the f of x faces it down now. So it's now downward facing. It just reflects from where it was down to where it is. Okay? So now let's talk about f of x plus 3. So let's compare this to the original. So it's still facing up. Nothing's changed there. Now, let's check where it was at 1. Okay, it was here. Now it's moved 1, 2, 3 places over. But it hasn't moved to the right. It's moved to the left. So something's weird here. So now my transformed function, we have f of x plus 3. So this plus 3 is in the parentheses with the x, which means that if I did have f of x is 2 to the x, now I have 2 to the x plus 3 all in the exponent. So if it's plus 3, but it's moved 3 to the left, I'm going to put the graph has shifted to the left 3 places. So when I change just the x-coordinate within that exponent, it's opposite. Does that sound familiar to you? Okay, remember in quadratics, when I had the f of x equals the x minus h squared, a times x minus h squared plus k, that h in there tells me it's the opposite of what it should be. So if it's plus 3, you would want to move it to the right 3, but it's actually to the left 3. Okay, so it moves it to the left 3 places. Now let's look at this one. F of x minus 3, where do you think this one's going to move? Okay, let's check. So if we check where it's at 1, it's now 1, 2, 3 places to the right. So the transformed function here, f of x minus 3 is the same thing as 2 to the x minus 3. So the graph shifted 3 units which way? Yes, this time it shifted 3 units to the right. Okay. So when it's within the parentheses, it's moving it left and right. Okay, we're going to kind of compile all of these in just a second. So then f of x minus 3, this time you have the f of x separately and then the minus 3 out to the side. It's not in parentheses. So that means I have 2 to the x and then minus 3 separately. So if it's out here, that actually moves it up or down. So it was at 1, now it's at 1, 2, 3. So that would be 2 to the x minus 3. So the graph moved down 3 units. Okay, so if it's outside of here, this minus 3 means that it's moving down 3 because it's separate from the x. So it's kind of like we're taking all the y coordinates and shifting them 3. Whereas these, the f of x plus 3 and the f of x minus 3, we're changing the x coordinates by 3. So that moved it either to the left or the right. But the f of x minus 3 like this is not affecting the x, it's affecting the y. So it moves it up or down by 3. Okay, let's continue. So now we have f of x plus 3. So what do you think is going to happen here? Okay, so the transformed function here would be 2 to the x plus 3, which means it's going to be shifted up 3. 1, 2, 3. So the graph was shifted up 3. Okay, and then the 3 times f of x. Now let's think about my quadratics. In my quadratics, when I multiplied by something, okay, when I multiplied by something in my quadratics, it was a vertical stretch or a vertical compression. If it was multiplied by a number that was greater than 1, then it was a vertical stretch because it made those y values get bigger faster. But if it was multiplied something whose absolute value is less than 1, so like 1/2, 1/4, and so on, a fractional or a decimal value, then that was a vertical compression because it pushed it down. Okay, it wasn't growing as fast. So 3 times f of x is the same thing as 3 times 2 to the x. Okay, so that's a vertical stretch So the graph was vertically stretched by a factor of 3. Okay, so the graph was vertically stretched by a factor of 3. So it was at 1, now it's at 3. It was 1 times 2, which is at 2, but now it's at 6. Okay, so each of those y-coordinates have been multiplied by 3. So our table was 0, 2 to the 0 is 1, and 2 to the first is 2, and 2 to the second is 4, and 2 to the third is 8. But now each of these y-coordinates have been multiplied by 3. So it's at 0, 3, and 1, 6, and 2, 12, and 3, 24, and so on. So all of those are 3 times as much as they were because of this 3 out here. Okay, so it's my y-intercept, but it's also a vertical stretch. So let's go over here to let's practice. So describe how k affects the graph of the function f of x equals 2 to the x in each of the following situations, and assume that k is greater than 1. So f of x minus k. So that function would be 2 to the x, so that would be 2 to the x minus k. So when it's minus k, it's going to move it down. So it's going to move the graph down. So the graph shifts down k units. Okay. So then f of x plus k would be 2 to the x plus k. So that would shift it to the left k units. Because remember, it's opposite when it's there. Okay, k times f of x, and all of these say assume k is greater than 1. So if k is greater than 1, that means that it's a positive, it's not a fraction. So for k times f of x, it would be k times 2 to the x. So it would mean the graph is stretched vertically, or vertically stretched by a factor of k. The function g of x represents an exponential function. The ordered pair 6, negative 3 lies on the graph of g of x. The function f of x equals g of x plus 5. Name a point on the graph of f of x. So this g of x plus 5, okay, the g of x plus 5 means that I'm adding 5 to the y values, or the g of x values. So that would mean that I take the negative 3 right here. I'm starting with 6, negative 3. This is my g of x. Okay? But I'm adding 5 to my y coordinate. Because remember, this point right here is like the point x, g of x. Okay? So it's my x input and my g of x output. So I'm going to take that negative 3 and I'm going to add 5 to it. Well, negative 3 plus 5 is 2. So it's actually now the point 6, 2. Okay, so that would be my answer because the 2 is the negative 3 from here plus 5. Now we have the function h of x equals g of 2x. Name a point on the graph of h of x. So this x in here is being multiplied by 2. So that would be like g of 2, so this g of 2x, so I'm looking right here, then that would mean h of x equals, so what we know right now is that g of 6 is -3, okay? So we're trying to actually find what this x is so that will help us know how to break this down a little better, because g of 2 times x is equal to h of x. So 2 times x, well, this is the same thing as 2 times 3 is equal to -3. So 2 times 3, so my x must be 3, which means that h of 3 has to be equal to -3, because this is g of 2x and this is h of x, okay? That's that g of 2x equals h of x. So the point on this one would be 3, -3. So one more time just to backtrack, because that one's not nearly as straightforward as part A was. So g of 6 equals -3. That's what we know from this problem. Okay, so I got that from the 6, -3 right here. So g of 6 is -3. That's g of 2 times 3, because it's 2, it says right here 2x. So 2 times something. So the way I get 6 from multiplying by 2 is 2 times 3. Well, this is still equal to -3. So this is my 2x. So then I take my x, my 3, and I put it here. So that's h of 3 is -3. So the point on that one would be 3, -3. Okay? So let's look at the try it. If you're doing this in class, then please pause right here until everyone's done with this part, and then you can replay the video. I'll give you a second. Okay, so recall the graph of f of x equals 2 to the x. Describe the graph of f of x minus 3 plus 2. Okay, so let's take this in pieces. So if I were to write the function, okay, the f of x minus 3 plus 2. This function would be 2 to the x minus 3 plus 2. Okay, so with all of this included, this minus 3 right here means it shifts or translates, would be my geometry word there, translates to the right. Don't forget that it's backwards here. So it translates to the right 3 units. And then it shifts up, because this plus 2 means it shifts up 2 units. So to the right 3 units and up 2 units. Okay. The following graph represents the function f of x. F of x is a transformation of the exponential function g of x equals 2 to the x plus 1. Write an exponential from the exponential function for the graph. So 2 to the x plus 1. Let's talk about what that would look like. So 2 to the x plus 1, if we were to graph that, I'm going to see x and g of x. Okay, so if I were to graph this at 0, 2 to the 0 is 1, plus 1 is 2. So I'm at 0, 2. And then if I were to put 1, 2 to the first is 2, plus 1 is 3. And then if I were to put 2, 2 to the second is 4, plus 1 is 5. 3, 2 to the third is 8, plus 1 is 9. And you could even go backwards from there. But this is at 0, 2. If I were to put -1, just for fun, then that is 1/2 plus 1, which is 1.5. And then -2, that is 1/4 plus 1, 1.25. So it's going to be approaching 1. So I'm at 0, 2, 1, 1, 2, 3, 2, 1, 2, 3, 4, 5, 3, 9, 2, 3, 4, 5, 6, 7, 8, 9. Okay, But then if I go this way, I'm at negative 1, 1.5, and 1.25, and so on. So it's going to be approaching my 1. So this was my original graph. This was my g of x, which is 2 to the x plus 1. Okay, now my graph has been shifted in some different ways. So it was, we can tell that there has not been a vertical stretch by simply looking at, from here, it's at 1 over and 1 up. So 1 over, 1 up. And 2 over, it's 1, 2, 3 up. 1, 2 over, it's 1, 2, 3 up. So it still has the same general shape. It's not any steeper, it's not any less steep, it has the same shape. However, I can tell that my asymptote has shifted 1, 2, 3, 4 units down. Okay, my asymptote has shifted 4, let's see, 1, 2, 3, 4 units from where it was. So, sorry, not from here, from 1, 2, 3, 4 units to my asymptote. So if it went down 4 units, then I'm going to take this graph, I'm going to take this g of x, and I'm going to subtract 4. So f of x is equal to g of x minus 4 because it shifted down 4. So that means that I have what my g of x was equal to, my 2 to the x, plus 1, and I'm taking away 4 from this, which means that f of x is equal to 2 to the x minus 3. And we could test that on this and see if that's true. So if I wanted to take this, I could take the point 0, negative 2, and I could test it. By saying 2 to the 0 minus 3. Well, that's 1 minus 3, which is negative 2. I could test the point 1, negative 1. So 2 to the first is 2 minus 3 is negative 1. And you could go on just to be sure that you have the right function. But it is, in fact, f of x equals 2 to the x minus 3 because it's shifted down 4 from the original g of x, which is 2 to the x plus 1. So you could do that just by graphing the original and then going from there. You could do that by knowing your end behavior or where your asymptote would be and then simply counting from there. However you would like to do that. So let's go on to the beat the test. Consider the function f of x equals 1/2 to the x. So let's describe the graph of each transformation. So g of x would be f of x plus 2. So my g of x here would be 1/2 to the x plus 2. So this time, my graph is being shifted 2 units to the left. Okay, because the plus 2 normally would mean we go to the right, but this time it means we go to the left. Okay, this minus 2 here means that I shift it up or down because it's being taken away from my y value. So to write that function, the h of x function here would be 1/2 to the x and then minus 2. So it shifts down 2 units. So it's a translation of 2 units down. The negative 2 times f of x, so m of x, equals negative 2 times 1/2 to the x. So there's 2 things going on here. It's reflected across the x-axis. That's because of the negative. And then because of the 2, it's a vertical stretch by a factor of 2. Okay, so it's reflected across the x-axis and stretched vertically by a factor of 2. Okay, if we have the f of x minus 4, then that's n of x is equal to the 1/2 to the x minus 4, which means it shifts right 4 units. So it shifts to the right 4 units because it's the opposite of this. And then the f of x plus 3 would be 1/2 to the x plus 3. So shifts up 3 units. Okay, so there we are. Let's recap one thing quickly. Just we've used it throughout, but I kind of want to have this written down for you. So the standard form of an exponential. Okay. F of x equals a times, f of x equals a times r to the x minus h plus k. So before we had this idea of a vertex, and this was vertex form. Very similar here. It's kind of your turning point. It's that point right above the asymptote. So for this h moves us left to right. Okay, but it's the opposite. And then the k moves us up and down. So you might want to put a note here that it's the opposite of what you think. And then the a is a vertical stretch or compression. And then a negative a, one more thing, would be a reflection. So if that a is negative, it flips it up or down. So that's kind of the recap for the lesson here, that with an exponential, the h still moves it left to right. So if you're doing anything just to the h, so on the inside, then that moves it left to right, but it's opposite of what you think because this is x minus h. The k moves it up and down. The a is a vertical stretch or compression, and then negative a is a reflection. If you have any questions, shoot them my way.